Alright, hello everyone. Let's look at an example of an RC circuit problem. So, looking at the RC circuit drawn, where the resistance of the resistor is 1000 ohms, the capacitance of the capacitor is 5 millifarads, and the voltage of the battery is 45 volts, calculate part A, the time constant of the circuit, B, the maximum charge on the capacitor after the switch is closed, and part C, the current in the resistor 5 seconds after the switch is closed. Okay, so for part A, we're looking for the time constant, which is this variable called tau, and it's just equal to R times C. So pretty straightforward. We're going to take the resistance of 1000 ohms, or 1 kilo ohm, times the capacitance of 5 times 10 to the negative third farad, and we're going to get an answer of 5 seconds. So tau, the time constant, is a measure of time, so we have 5 seconds. For part B, we're going to calculate the maximum charge on the capacitor after the switch is closed. So we're looking for Qmax, the maximum charge. And that's also pretty straightforward. It's just the capacitance times the voltage. So the capacitance of 5 times 10 to the negative third farads times 45 volts. And this gives us 225 times 10 to the negative third coulombs, or 0.225 coulombs. Okay. And for part C, this part is a little tricky. We're looking for the current in the resistor at t equals 5 seconds. Okay? After the switch is closed. So this part right here, after the switch is closed, we're starting with the switch open, and if in that case, the capacitor is going to charge up. So if the capacitor is charging, we're going to look at this equation. Little q equals capital Q times 1 minus e to the negative t divided by tau. So with this given equation, we can calculate little q here. So using Qmax of 0.225 coulombs times 1 minus e to the negative 5 seconds divided by tau, which we calculated to be also 5 seconds. Let's see, we get that Q, the charge on the capacitor, 0.142 coulombs. Okay, so this doesn't give us our current through the resistor, so we're taking a little bit of a roundabout way to get there. But now that we have this, we can calculate the voltage on the capacitor. So to do this, we're just going to take little q over C, so 0.142 coulombs divided by 5 times 10 to the negative third farads, which equals 28.5 volts. Okay, and now here's where things start to come together. If we just had this circuit without the capacitor, the voltage that's getting used by that resistor would be the total voltage, the 45 volts. But because we have this capacitor here, some of the energy, if volts is also joules per coulomb, so some of this energy, this joules, is being used by this capacitor. So not all the voltage will be in the resistor. So what we did figure out is the voltage used by the capacitor. And the part that makes sense is the total voltage has to equal the voltage of the capacitor plus the voltage of the resistor. So since we have the total voltage of 45 volts, and we just calculated the voltage of the capacitor, we can now calculate the voltage through the resistor. So simply rearranging that equation, we come up with this. And we find that the voltage through the resistor is going to be 16.5 volts. So now that we have this, we can finally find the current through the resistor. And we can do that through Ohm's law. So Ohm's law is that V equals IR. Okay, so we can just rearrange this to find I, which is what we're actually looking for, which equals VR divided by R. Okay, so the current is then 16.5 volts divided by the resistance of 1000 ohms, and we get that the current through the resistor is 16.5 times 10 to the negative third amps, or 16.5 milliamps. Alright, thank you all for watching.